Hello, I am Dr. Sudha, Associate Professor, Department of Mathematics, Government Science College, Autonomous, Bengaluru. In this session of Algebra-I, Unit 1, let us discuss isomorphism theorems. So the first isomorphism theorem is stated as, let phi be a homomorphism on G onto G bar with kernel K. Let n bar be a normal subgroup of G bar and n is equal to set of all G belonging to G such that phi of G belongs to n bar. Then we need to prove that G by n is isomorphic to G bar by n bar and G by n is isomorphic to G by k by n by k, which is also known as the Freshman's theorem. So let us prove the first one, that is G by n is isomorphic to G bar by n bar. So let us consider the given set n is equal to set of all G belonging to G such that phi of G belongs to n bar. And it is also given that n bar is normal in G bar. Now let us prove that this set n is normal in G. So for that, let us consider n belongs to n and G belongs to G. Our intention is to show that Gn, G inverse belongs to n. Since n belongs to n and phi is a homomorphism from G onto G bar, phi of n will belong to n bar by the given set n. Then when G belongs to G, we can say that phi of G belongs to the codomain group, that is G bar. Now let us show that G and G inverse belongs to n. Phi of G and G inverse, if we consider, since phi is a homomorphism, we can write this as phi of G into phi of n into phi of G inverse. And later on, this phi of G inverse can be written as phi of G whole inverse using one of the properties of homomorphism. Since phi of G belongs to G bar and phi of n belongs to n bar, so this is an element of n bar. Since this is an element of n bar, that is image of G and G inverse is an element of n bar by the given set n, if the image belongs to n bar, then the element will belong to n. Therefore, G and G inverse will belong to n. Therefore, giving us that n is normal in G. Next, let us define a mapping psi from G to G bar by n bar, as we need to show that G by n is isomorphic to G bar by n bar. Here we are taking from G to G bar by n bar. If we are able to show that this psi is a one onto homomorphism and with the kernel n, then we are done with the result because of using the fundamental theorem of homomorphism. So let us define psi as psi of G is equal to n bar of phi of G, because G bar by n bar is the quotient group here. So it will contain the cosets n bar into phi of G for all G belonging to G. Now we need to show that this psi is well defined. So let us assume the two elements are equal, that is A is equal to B, where both A and B belongs to G. We need to prove that psi of A is equal to psi of B. Since A is equal to B and phi is a homomorphism, we know that phi of A will be equal to phi of B. And this in turn gives us n bar of phi of A is equal to n bar of phi of B by the definition of cosets. Because the elements are equal, then the cosets generated by them are also equal. Since now n bar of phi of A is equal to n bar of phi of B, by the definition of the psi, we get psi of A is equal to psi of B, therefore giving us psi is well defined. Now, next let us prove that psi is homomorphism. For that, let us consider two elements A and B belonging to G. Consider psi of AB. By the definition of psi, this will be n bar phi of AB. But phi is a homomorphism. Therefore, we get n bar of phi of A into phi of B. And this is a coset generated by AB. Therefore, we can write this as phi of n bar of phi of A into n bar of phi of B by the properties of cosets. And here, this gives us psi of A, and n bar of phi of B gives us psi of B. Hence, psi of AB is equal to psi of A into psi of B. Hence, psi is a homomorphism. Now let us show that this psi is onto. So let us take an element n bar into G bar in the codomain, that is G bar by n bar. Since n bar G bar belongs to G bar by n bar, this element G bar will belong to the codomain group of phi, that is G bar. Since this is an element of the codomain of the mapping phi, there exists an element G belongs to G such that phi of G is equal to G bar, because phi is given to be an onto homomorphism. Therefore, n bar G bar now can be written as n bar into phi of G, and this in turn gives us psi of G. Therefore, for every element n bar G bar in G bar by n bar, there exists a G such that it is equal to psi of G. Therefore, psi is onto. Now we have proved that psi is onto homomorphism. Now it is enough to consider the kernel of psi and show that it is equal to n. So kernel psi will be the set of all elements belonging to the domain G such that the image of all those elements is the identity element of G bar by n bar, that is n bar. So it is set of all G such that since psi of G is equal to n bar, it is nothing but n bar of phi of G is equal to n bar. So n bar of phi of G is equal to n bar is similar to the coset HA is equal to H. That implies that A belongs to H. Therefore, the element phi of G must belong to n bar. Since phi of G belongs to n bar, this element G will belong to n. Therefore, this is the set which is the given set n. Therefore, kernel of psi is equal to n. Therefore, we have a onto homomorphism psi from G to G bar by n bar with kernel psi is equal to n. Now let us make use of the fundamental theorem of homomorphism. Therefore, by FTH, that is the fundamental theorem of homomorphism, it follows that G by kernel of psi, that is n, is isomorphic to G bar by n bar. So this proves the first part of the theorem. Next, let us prove that G by n is isomorphic to G by k by n by k. For that, let us consider a mapping theta from G to G by k by n by k, and let us define this theta as theta of G is equal to n by k of kg, because this kg is the element of G by k, and n by k will be the normal subgroup in G by k. Therefore, we consider the coset n by k of kg for all G belonging to G. First, let us prove that theta is well defined, that A is equal to B, where A and B belongs to G. Since the elements are equal, then the cosets generated by these two are equal. Therefore, Ka will be equal to Kb. Since Ka is equal to Kb, these are the two elements equal. Therefore, the coset generated by n by k of Ka is equal to n by k of Kb. Since these two are equal, then by the definition of theta, this is theta of A is equal to theta of B. Therefore, the elements are equal implies the images are equal. Therefore, theta is well defined. Next, let us prove that theta is a homomorphism. For that, let us consider two elements A and B in G. Consider theta of AB. Since theta is defined as n by k of AB, Now this K of AB can be written as Ka into Kb. So we get theta of AB is equal to n by K of Ka into Kb. Now this is the coset generated by Ka into Kb. Therefore, you can write this as n by K of Ka into n by K of Kb. Now by the definition of theta, this will be equal to theta of A and this is theta of B. Therefore, theta of AB is equal to theta A into theta B. Therefore, theta is a homomorphism. Now let us prove that theta is onto. So for that, let us take an element n by K of Kg in the codomain. And let us show that there exists an element in the domain such that theta of G is equal to n by K of Kg. So let us consider n by K of Kg in G by K by n by K. So this implies that this Kg belongs to G by K. Since Kg belongs to G by K, this G belongs to G. Therefore, there exists a G in G such that Kg belongs to G by K. Therefore, n by K of Kg will be equal to theta of G. Therefore, theta is onto. Now, theta is onto homomorphism. Now, let us check what is the kernel of theta. So, kernel of theta is set of all G belongs to G such that theta of G is equal to identity of G by K by n by K. Identity of G by K by n by K is n by K. Therefore, we take theta of G is equal to n by K. But what is theta of G? This is n by K of Kg. And that is equal to n by K, which is similar to HA is equal to H. Therefore, A must belong to H. So, n by K of Kg is equal to n by K implies this Kg must belong to n by K. Since Kg belongs to n by K, this element G must belong to n. So it is set of all G belongs to G such that G belongs to N. So this gives us the set N. Therefore, theta of G, that is kernel of theta is N. Therefore, theta is a mapping from G to G by K by N by K, which is an onto homomorphism with the theta, kernel theta is equal to N. Now, once again, using the fundamental theorem of homomorphism, it follows that G by, that is the domain by the kernel, that is N, is isomorphic to the codomain G by K by N by K. Hence, it proves the first isomorphism theorem. Now, let us move on to the second isomorphism theorem. If N and M are normal subgroups of a group G, then we are required to prove that Nm by M is isomorphic to N by N intersection M. We know that whenever N is normal in G and M is normal in G, we have proved these results. That is, Nm is a subgroup of G, N intersection M is normal in N, M is normal in Nm, and Nm is equal to Mn. Therefore, we can think of Nm by M, the quotient group, as well as N by N intersection M. Once again, this is also a quotient group exists. Now, let us define phi from Nm to N by N intersection M. Because here also we are going to make use of the fundamental theorem of homomorphism. So, let us define a mapping phi from Nm to N by N intersection M by phi of Nm. Nm is an element of the domain Nm and that is mapped on to N intersection M of N, where N intersection M is the normal subgroup of N for all N belonging to N and M belonging to M. First, let us prove that phi is well defined. Since phi is a mapping from Nm to N by N intersection M, let us take two elements in the domain Nm. So let us consider N1 M1, N2 M2, which belongs to Nm. Since we know that Nm is equal to Mn, we can write any element N1 M1 as M1 N1 and N2 M2 as M2 N2. Now let us take these two elements are equal and show that their images are also equal under phi. N1 M1 is equal to N2 M2. Let us operate with M1 inverse from the right side. So this gives us n1 is equal to n2 m2 m1 inverse. And this n2 m2 m1 inverse will definitely belong to n2 m, because m2 and m1 inverse belongs to the set m. So this belongs to n2 m. But n2m can be written as mn2, because nm is equal to mn and m is normal in G. Now this n1 will belong to mn2, implies that n1 is equal to small m into n2, where this small m belongs to the normal subgroup capital M. Now we can write this as n1 m2 inverse is equal to m by operating by n2 inverse from the right side. But n1 n2 inverse belongs to n, and n is a subgroup of G, right? Because of this reason, now this element n1 m2 inverse belongs to m as well as it belongs to n. It implies that it belongs to the intersection, that is n intersection m. Therefore, n intersection m of n1 n2 inverse, that is the coset generated by this element n1 n2 inverse, will be equal to n intersection m. Now let us write this as by operating by n2 on either side from the right side, we get n intersection m of n1 is equal to n intersection m of n2. But by the definition of phi, this is phi of n1 m1 is equal to phi of n2 m2. Therefore, phi is well defined. Now let us prove that phi is a homomorphism. For that, let us take two elements from Nm, that is n1 m1 and n2 m2. So let us consider phi of n1 m1 into n2 m2. And this now can be written as n1 n2 m1 m2, because this element m1 n2 now can be written as n2 m1, because nm is equal to mn. And this in turn now can be written as phi of n1 n2 into m, where m is the product element m1 m2 and this belongs to m. Now this, by the definition of phi, can be written as phi of n1 n2 m can be written as n intersection m of n1 n2. And this is the coset generated by the product element n1 n2. Therefore, this can be written as the product of two cosets, that is n intersection m of n1, n intersection m of n2. By the definition of phi, this will be equal to phi of n1 m1 into phi of n2 m2. Therefore, we have shown that phi is a homomorphism. Now we are required to prove that phi is onto. For that, let us take an element in the codomain, that is n by n intersection m. So let us consider n intersection of n, which belongs to n by n intersection of m. Here this n belongs to n, and this n can be written as n into e, because e is the identity. So NE now will belong to NM, because N belongs to N and E belongs to M. So this is an element of NM, that is N is an element of NM. Let us consider phi of NE. So by the definition of phi, this will be N intersection M of N. So for every element N in N, we have shown that there exists an element NE such that phi of NE is equal to N intersection M of N. Therefore, phi is onto. Now let us consider what is kernel of phi. Kernel of phi will be the set of all Nm belongs to the domain Nm such that phi of Nm is equal to the identity of the codomain, that is N by N intersection M. Now we can write this set as Nm belongs to Nm such that phi of Nm is N intersection M of N, and that is equal to identity of N by N intersection M, that is N intersection M, which is similar to H. A is equal to H. Therefore, A belongs to H. So here N intersection M of N is equal to N intersection M. Therefore, this element n must belong to n intersection m. Now, this n belongs to n intersection m implies that this n belongs to both the sets n and m. Let us consider this n belongs to m. So, m belongs to nm and n belongs to m. Therefore, both n and m will belong to m. Therefore, this gives us the set m. So, kernel of phi is the set m, that is the normal subgroup m. Now, phi is a homomorphism from nm on to n by n intersection m with kernel phi is equal to m. Therefore, let us use the fundamental theorem of homomorphism, and it follows that the domain, that is n m, divided by the kernel phi, that is n, is isomorphic to n by n intersection m. Hence, this proves the second isomorphism theorem. Thank you.